Hi everybody, welcome to this submersive training course about design smaller, lighter, more efficient motor drives with EPC motor reference designs. I'm Marco Palma, I'm Director of Motor Drive Application and Efficient Power Conversion, and I will show interesting slides about what we offer in terms of reference design. To have a better view, I will switch off my camera, and so I will show the entire presentation. Then I will switch on again after the end of my presentation. So starting from the meat, there is one important thing, which is there is a benefit to using GaN device in brushless DC motor drives. So, and the reason is that experimental validation showed that you can get higher system efficiency with gallium nitride inverter, lower audible emissions, improved precision, lower torque ripple, and smaller size. And the other two important thing is with the GaN FET and the integrated circuit based on gallium nitride, you can have faster switching and zero reverse recovery. What does it mean? If you increase the switching frequency, then you can reduce the input capacitance. So, and also if you have some inductance, you can reduce it. And maybe you can also reduce the electrolytic capacitors. On the other side, reducing the dead time, it helps in having a higher torque per ampere on the same motor. And these two things together improve inverter and motor overall system efficiency. And also reduce size and weight by integrating an inverter inside the motor. So here you have an overview of the existing reference design as of today. There are smaller boards like the EPC 9146, which is based on an integrated circuit called EPC 2152, and also the upcoming new EPC 9176, which is based on the new EPC 23102 integrated circuit. And then we also have slightly bigger boards like EPC 9167 HC, which is based on GaN FET EPC 2065, and the EPC 9173, which is based on the EPC 23101 integrated circuit. Together with this board, they all share the same connector. You can make available microcontroller existing boards, like this is a PIM from a microchip on a DSP33. This is a ST Nucleo, and this one is a Launch XL from TI. We're just doing adapter boards for each of them so that you can connect to each of these reference design and have a seamless experience and go directly and test with your motor. So let's have a look on EPC 9146. Just for your info, the 9176 is really similar from that point of view. Only one thing is different, I may say. And it looks like from the top side, this is how it looks like from the bottom side. And you can see that there's main power connection for the DC bus, motor connection here on the bottom of the board. There is housekeeping power supply. So once you connect the power from the DC bus, everything is already generated on board. This is the gallium nitride power stage. As I told you, these are three integrated circuits. There are the threaded standoff for heat sink mounting. And there is current sense for this board. It's 1.5 million in series to the phase of the motor. There is also an interface for the Hall and encoder. And in the 9146, you still have a provision for optional harmonic filter. Actually, this filter is bypassed. In the 9176, there is not. The reason is all these years we didn't see big utilization of the harmonic filter, so we really decided to remove from our reference design. And this is the control connection. The measure we're talking about 8 centimeters by 7.5. if we look at 9167, which is similar to the 9173, here is the bottom side, this is the top side. It comes with a main power connection, motor connection, housekeeping power supply. In this example, only 5 volts are needed for this board because also the gate driver is living only on 5 volts. And then there are the gallium nitride inverter. In this case, it's discrete plus gate drivers and optional anti-freewheeling diodes. In the HC version of 9167, we have 2 GaN FET in parallel. In the regular version 9167, we just have 1 GaN FET per switch. And in 9173, there's a difference. Gate driver is not there and available anymore because it's simply integrated inside the integrated circuit. We have a lot of capacitance because we don't know exactly for what we are going to use this reference design. But main point, and I will show you also a little bit better, definitely you don't need all this capacitance on the DC bus, and you don't need it also on the switch itself. So the board itself can be easily simplified, and you can remove the capacitance you don't need. And also this board comes with a threaded standoff for the heatsink mounting. Actually, all these boards come with a heatsink already mounted. If you want then to have an idea of how the things perform, how our GaN FET and our integrated circuit perform without heatsink, you just can unscrew the heatsink and remove it and see what happens, okay? We have current sense shunt in phase 1 million in series to the phase, or we also have, obviously we have current sense amplifiers on board, and we also have a current sense shunt also on the leg, because this is giving the option to measure either the current sense on the source of the leg or in the phase of the motor. And then there's a controller connector as in the other board. How do we do the thermal implementation? As I told you, there are threaded standoff. So we have the heatsink, there is a nice insulating material, there is a thermal interface, insulating material. There are 3, 1 per each switching cell, which is made to remove the heat and go to the heatsink. And it's very efficient design because the thermal resistance of these devices from the active area to the top, it's very low. It's between 0.2 degrees Celsius per watt up to 0.4. From controller point of view, with the microchip solution, you can use motor bench, so you can use MPLAB, you can use a motion control configurator, then use the motor bench development suite, and you can take advantage of doing automatic code generation by simply inputting the motor parameter inside the system. For the ST motor control workbench, similar story. You can use the motor control workbench, put the motor parameter inside the system, and then get the code automatically generated for you. And then you can also get advantage of the graphical user interface so that you can drive the motor either by just pushing this button on the board, but also by playing with the graphical user interface and do a quick evaluation of the system. Let's look quickly how it is. Our reference design are quite similar, so all of them have half bridges, have voltage sense. They have measuring current for the leg and or for the phase, and then there is overcurrent protection, and then there is a voltage sensing power supply for the controller and for the gate driver. The controller is not on board, is connected from the controller interface board. If we look on the gallium nitride inverter basic schematics, you see that you need low and middle frequency capacitor, then you need a high frequency capacitor, and then there are your switches. And this is exactly the example of 9167 HC, where you have the DC bus capacitor for the low frequency. Then you have the switching cell. The switching cell is how it looks like. These are the high side GaN FET in parallel. These are the low side GaN FET in parallel. And so in the 9167 HC, we have two in parallel. These are high frequency capacitors. And on the bottom, you can see the middle frequency capacitor of the gate driver and the optional freewheeling diodes. One comment on this: these are the leg shunt for measuring the current in the leg connected to the source of the low side, in case you want to test the source shunt measurement system. I have one other comment on this one. One other comment here is that all these capacitors are definitely really redundant because we don't know how you're going to use the board, but we tested the board with only 9 capacitor on the DC bus for a total of 19 microfarad, 90 total. We removed all the high frequency capacitor and all the middle frequency capacitor, and we got a very good operation, still a very good operation. So stay tuned, because in the future we may have other news about motor drive application, reducing the capacitor that are needed. And with 19 microfarad in steady state, then you have to take care of the transient if you have a very fast acceleration. Otherwise, you don't need all the capacitors that are in our reference design. So before just scoping the reference design, please have a look really on what is needed in your application, and maybe you can also do some new experiment and remove these capacitors. Continuing on the presentation, you see this is the switching cell for the 9146. It is almost similar also for the 9176. In the 9146, you have the EPC2152. In the 9176, you have the EPC23102. And this board is capable of 10 amps of RMS at 48 volt 100 kilohertz, the 9146, while the upcoming 9176 is capable of more than 15 amps RMS. This is instead the 9173 based on EPC23101. Each of these devices is like this. There is a gate driver and then a side FET. So we're using one for the high side and one for the low side. And how do we do it? This is the high side FET. This is the low side FET. This is the phase going to the motor, and the gate driver function is distributed between the two integrated circuits. And then here we have a leg shunt to choose either leg shunt or source shunt. So yes, source shunt or phase shunt. And as you can see, since we're using the high side also on this gate driver, this node can float up and down with respect to the power ground without altering the digital input portion. And the high frequency capacitor are in the middle between the two parts. We are currently testing now, removing all of them and seeing if effectively they're needed or they are redundant, and we can remove it and reduce the bill of material. Regarding the shunt sensing, we have a phase shunt and we have leg shunt. That is simply an option. It's not usually in a reference design for motor drive. Either you have one or the other, and you don't need both. But it just, you can choose by, you have jumpers here, here, here. By putting a jumper, the right jumper, either you measure and amplify the signal coming from this, or you do it from the signal coming from this. From the controller point of view, the gain is the same. It's always 20x. So, and the resistance here is 1 million, and also these are 4 parallel of 4 million, so total 1 million. So from the controller point of view, it's completely transparent. It's depending really on the choice. If you're using in-phase current measurement, then you need sophisticated common mode rejection system. If you're using a leg shunt, then you're not experiencing the common mode, but then you need 50 megahertz operation amplifier to easily measure correctly at the right point the shunt. And here is how we do the sensing. We make a cage, Faraday cage of analog ground on top of one layer, and then you have the signal that are connecting to the leg, which are again surrounded by analog ground. And then in the other layer, also we have a closure of the Faraday cage or the analog ground in order to really protect this low impedance source signal coming here. And then this is the area where you have the amplification of the operational amplifier. And one important point is that the power is flowing from here to here, is not flowing here. That's why you can get this low ohmic source signal coming here, and then you can process and then go to the left to the controller. And if we look on how it looks like, this is the current flowing into the motor, positive going to the motor, negative coming back. Sorry, this is the current. So negative coming back from the motor, positive going to the motor. And this is the envelope of this one. So this is the zoom of this picture. And when you have this signal here, which is 1.65 volt, it means current is 0. Obviously, the phase shunt amplified signal is always available and exactly just in opposition of phase to the current, while the real current, which is measured with a probe, while the source shunt signal is available and has the same value of the phase shunt signal only when the low side GaN FET is on. And from this picture, you can see that the signals are very good, and they are correctly measured by the controller. So let's have a look on some experimental setup. So the main point here is just to give you an idea of how this board works. We have several types of boards, and once you have an idea, then you can think which one may be the right one for your application. We tested our board both without heatsink and with heatsink, always without air conduction, and we are considering to have only 50 degrees delta from the temperature on the ambient to the highest temperature of the active area of the devices. So here in this setup for the 9146 board, you see that there is a motor, and then there is an hysteresis brake dynamometer, and then there is the setup with a board that can go up to 10 amps of RMS with the heatsink, and up to 6 amps of RMS without this heatsink, if you allow not more than 50 degrees delta from the active area to the ambient. And these are measurement probes for setup. For the 9167 board, we did a just slightly different setup. We're running 100 kilohertz, 25 amps of RMS on a hub front wheel pedelec bike motor. We're running it in open loop, and we also open the motor so that it's really working mainly like as a kind of overflux motor, and these are motor parameters. Okay, this motor is made to run 32 kilometers per hour in a 26-inch wheel e-bike. And we tested again also this one with and without heatsink. So for the small EPC 9146, as I told you, we can get 10 amps RMS at 100 kilohertz with very small dead time, 21 nanoseconds. For the biggest board, we can get up to 30 amps RMS, 100 kilohertz, and the dead time is still slightly bigger, it's 50 nanoseconds, but it is nothing compared if you compare to conventional board with MOSFET, where usually you have 500 nanosecond factor, and then also MOSFET cannot go 100 kilohertz. They will dissipate too much in terms of switching dissipation. So the point is, what happens if you reduce the dead time? If you reduce the dead time, you see on the left you have 500 nanosecond dead time, on the right you have 21 nanosecond dead time. Here on the left you see discontinuities. These discontinuities are due to the dead time because you get discontinuity on the voltage source inverter during the zero crossing. And here you don't have any discontinuity. It's a very clean signal, very low harmonic distortion. And what is then the effect? We measure with a real torque transducer, we measure the torque spectrum of the real torque measured with the transducer. And here we get an harmonic, which is there because of the dead time. This harmonic is not there if you reduce the dead time. And so if the current is the same, flowing into the same motor, then the energy of this harmonic goes into the DC component of the torque. So at the end of the day, the net result is that you get, on the same phase current, you get higher torque from the motor. And this is going to play an important role in efficiency. And there's also another important point. If you go with MOSFET's 500 nanosecond dead time, you will see that in low, due to this noise and distortion, you will see that in a low frequency of the current, you have higher spectrum contact, which is more difficult to filter if you want to filter. So at the end of the day, there's less EMI on the gallium nitride if compared to the regular MOSFET. And other thing is, which are really important, is if you start going higher frequency, then what you get is, this is an example from 20 kilohertz, 500 nanosecond dead time, same condition, same motor. This is the input current from the battery. This is the input current at 100 kilohertz. This is the input voltage from the battery. This is the input voltage from 100 kilohertz. And here is the phase current. So all of this to say that if you look in this case, there is the need to have a bigger capacitance, but here you can just live with a smaller ceramic capacitor. And interesting thing is, mechanical power here looks to be slightly higher. Instead, here, given the same frequency and the same current, while here it's lower, but the input power is higher. So let's then look on a more comprehensive table where we measure the input power to the, so we have a system with an electrolytic capacitor on the left, 500 nanosecond at time, 20 kilohertz, running 400 RPM, 5 amps of RMS. And on the right, we have 100 kilohertz for, actually it's 21 nanosecond that time, 400 RPM, 5 amps of RMS. The most important thing, which is now, it is really one thing to consider, is not really the inverter, which is getting more efficient. If you look here, 98.5, 98.2, what really changes is that by giving a better voltage signal, which is more sinusoidal to the motor, then the motor is acting more like an ideal motor, and so it's getting higher torque per the same current. And at the end of the day, what is really increasing is the mechanical power, even that the speed is the same, it is increased the torque, and the mechanical power is higher. So then if you do the total overall efficiency, considering input electric power, output electric power, and then output mechanical power, then you get an increase in the efficiency of the overall system. Then proceeding to the next slide, you see that also there's another important thing related to the dead time, when you may really trigger some resonances in the system and create some noise, and then reducing the dead time, it's going to reduce these resonances and definitely reduce the acoustical noise. And this is an example which is exaggerated because it's 1 microsecond, and usually in those type of motors never used 1 microsecond, but it gives you the idea. On thermal performance, this is the 9146. As I told you, we measured them without heatsink, and you see we allow to decide that 6 amp RMS is the limit. We allow 50 degrees delta between ambient and the die, and this is the same board but with heat sink. And then in that case, we still allow 50 degrees delta, considering that there is the heat sink. And in that case, we can almost double the current, actually add 40% of the current. In 9167 HC, without heat sink, easily we can get 20 amps of MS by having slightly, actually in this case it's 60 degrees delta, and then by putting heat sink we can reach, in this case we have less than 50 degrees delta slightly, and the reason is because we measure the heat sink temperature and we consider the devices to be slightly hotter, and we can reach with this board 25 amp RMS, 100 kilohertz, 50 nanosecond dead time with natural convection. And to finish then my presentation, this is an example of the graph you can get coming from the documentation, which is enclosed with a board. You have the characterization without heat sink and with heat sink, and the delta temperature that we allow to have, and what is the behavior. So your solid lines are without heat sink, and dashed line are with the heat sink. And obviously all these tests are done without any convection. So it's really pure natural convection, either of the board or of the heat sink. If you compare as of today, I don't think there are other companies making reference design which can feed 20-25 amps of MS to the motor. This is motor phase. I believe that at the end of the day, most of the reference design stops around the 3 amps of MS or 5 amps of MS. Instead, with this efficient power conversion reference design, you can quickly jumpstart to the real power application and really have a good starting point that maybe you can simply copy, reduce a little bit the complexity by removing compact capacitors, because many of them, as I told you, are not really needed, and have a faster time to market for your application. I really appreciate your attention. I open now for question and answers, and I hope you enjoy this webinar series. And don't forget that we have the books and the books for, and also we just released an application book in the last period. Thank you very much.
Thank you, Marco.
Okay, thank you, everybody. Now we can go live and answer the question. I saw that there are already 2 questions, and one of the 2 questions I actually asked for more clarification because I was not able to understand exactly what was the purpose, but the question is about on if there is any kind of load pulling in effect when we're doing the test due to the output ripple.
and because if the load is changing or impedance varies due to different torque or operation current, so this can affect the output ripple or the smoothness of the ripple waveform. In reality, all the tests we've been doing, we've done with hysteresis dynamometer, bench at a fixed speed, and there is a kind of big volcano, and that's what really happens on the slide that you saw. There is clearly an effect really due to the electric part of the circuit. Is not really related to the load, because I can go to the slide and show the slide I'm talking about. One moment, I will share my screen. I need to push this button. I will share the screen so you can see. Share. One moment. Okay, this is the slide I'm talking about. In this slide, at the end of the day, you see the dynamic of the mechanics. Here, this is one electrical cycle of the motor. In this case, the motor was a 4-pole pairs. So there is no such variation that can influence the ripple, and vice versa. This ripple is not able to influence the mechanics at that level. So it's really the electrical part of the motor that is involved into this, and then get for sure a better behavior when you are increasing the frequency of the voltage source inverter. The main point is that the more the total harmonic distortion is lower, so the better is this voltage you are sourcing from your inverter to your motor terminal, and then the better is the behavior of the motor that starts becoming like ideal motor the way it was designed for.
Okay, there is another question. Did you see that one?
There's another question from Katarina Ceramic, which is asking, do you have any information whether using GaN affects the iron losses in the motor, and how in comparison to MOSFET inverters? So I don't have it in this presentation, but I have already some simulation evidences on especially when it comes to higher voltage motors, because in this case the examples was on a 48-volt bus motor, and we are increasing the frequency of classical inverter and then going 48-volt. There are cases where we can go higher voltage, and we can even do more levels applied to the motor. And the main point is that either if you do multi-level, and then the effect of increasing the frequency by the multi-level system, or you do like in this example, 2-level system at higher frequency, you get two things on the motor. One thing is you start getting less ripple-induced iron losses. That is ohmic losses on the winding due to the fact that you have less ripple, and the higher is the current, the higher is the ripple, and then this type of losses go with the square of the ripple current. So definitely yes, it's not really related to MOSFET and GaN-FET. If you were able to run a MOSFET inverter 200 kilohertz, then you would have less losses in the motor due to the ripple. But the problem of the MOSFET inverter is that then you're getting a lot of losses in the MOSFET inverter. It's really related to the motor. The motor will definitely thank you if you increase the frequency for ripple-induced ohmic losses in the windings. And then there's another effect, which is also usually depends on the motor, but most of the motor are going into that direction. They get lower core losses, And so if you increase the frequency, you get lower core losses. Then at the end of the day, the motor is becoming more efficient. But to increase frequency, you need to have a technology that helps you doing it without paying too much in terms of losses. There is another question from Suresh Mukundan, who's asking, what is the DC bus voltage on this presentation? All the tests we've been showing in this presentation were done at 48 volt, and there are other tests that are done at 36 volt. The reason of 36 volt is because some tests were done for pedal assisted bikes, which are working on 36 volt battery. Some other are at 48 volt, focusing are mainly 48 and 96. Okay, all of these are kind of at the end of the day battery operated stuff. 96 is very well used in the industry, especially for some type of robots or cobots, and 48 is also well used in the industry, also in the automotive. There is Philip is asking, what about motor windings and DVDT? So the first thing I did when I started working with GaN-FET and I started working with motors, I come from the industrial world. I started working with IGBTs modules, then MOSFET modules, then discrete MOSFETs, then super junction high voltage MOSFET, and then I started working also on GaN-FET. When it comes to high voltage motor, for sure there are rules. You cannot go, let's say, in terms of DVDT on a 2-level inverter more than 5 volt per nanosecond. Okay. When it comes to low voltage motor, so what I mean by high voltage motor, I'm not talking about 400 volt DC bus motors, okay, and of 300 volt DC bus motor, 400 volt, 540, or even 600 volt motors. In that case, in my opinion, with this new technology, is kind of still keeping the 2-level structure. I envision a future going multi-level, but for several reasons. However, if you stay on a 2-level, then you have to do from 0 to 600 volt, then better doing not more than 5 volt per nanosecond. Then if you do the math, you understand that your switching cannot be faster than 120 nanoseconds. So you cannot have very small dead time. So in a low voltage arena is something different. A low voltage arena where you're working on a 48 volt motor, first there's no this type of rules that you have to fulfill the 5 volt per nanosecond, below 5 volt per nanosecond. However, in the industry, it's quite, there are 2 philosophies. There are usually motor manufacturers that they do manufacture their motors and also they do their inverters. They tend to go very fast. All the other usually tends to stay between 10 volt per nanosecond, 12 volt per nanosecond, no more than that. So I'm not going 100 volt per nanosecond or 200 volt per nanosecond like GaN-FET could do. I'm slowing the GaN-FET down and still getting an advantage over MOSFET because I'm getting a better voltage applied to the motor. I get a better figure of merit in terms of efficiency and in terms of dissipation. However, I'm not going super fast as the GaN-FET could do. That is also making the PCB layout a little bit easy. So that's the reason why I'm also saying on a presentation, there's no need to have all this capacitor we putting. Maybe the future board for motor drive will have less capacitors. So the number for you, it's around 5 to 10, actually 10 to 12 volt per nanosecond, no more than this. So do you have any, so this is a question, anonymous attendee, do you have any layout examples of a parallel operation using the new EPC 2302 type FETs? Will it possibly get continuous current like 65, 70 amps with these? The first question is, please be patient because it's my next board. We are already working on this, and we'll be having a board. The target is to get 4 EPC 2302 in parallel, and actually want to get more than 70 amps. So yes, I don't have it now to share it, but as soon as we'll have it, you will see for sure publication, and we will do advertising presentation. Okay, that's for sure. Then there's a question from Aditya. Actually, I believe is the same question as before. There was a question similar. I'm really limiting the DVDT to be in the range between 10, 12 volt per nanosecond. I'm talking about the DVDT which is imposed by the inverter to the motor. The motor, you can impose the active DVDT when you are actively switching on a device, switching events instead, which are dictated by the load and by the current, and that depends on the motor interwinding capacitance. So what I'm limiting the DVDT imposed by the turn on of the devices. So 10 to 12 volt per nanosecond. How much is propagation delay from controller and driver for 21 nanosecond that time? So the first thing is the propagation delay is matched on our system. So we make sure that we have the same propagation going in the low side and going in the high side, okay? So theoretically, you could have, for instance, 50 nanosecond propagation delay, even if it is matched. The most important thing is the matching of the delay. It can also vary, okay? But then if you have this type of propagation delay, which is matched on the low side channel and the high side channel, then you can still afford to have 21 nanosecond. Actually, in my test, I went down to 9 nanosecond at that time without any issue, because the most important point is not really the propagation delay from the controller to the switch, but is actually how the switch is switching and how predictable is the way it switch. And in another presentation, I was showing that really depends on the reverse capacitance of the device. The more it is non-linear, the more the way that the device switches, like a super junction MOSFET or a FET MOSFET, is switching in several segments. So it's really less predictable the way you can switch it. While the GaN-FET can switch very good way, very good predictable way, so you can go down to very small nanosecond time like this.
Okay, thank you. So there's a few more minutes if anybody else has any additional questions for Marco. There was one sent in ahead of time, Marco. I'm using a very high current motor with 48 volt input. Do GaN FETs parallel okay?
Sorry, I was on mute. Sorry. So can you repeat the question? The question is asking if it is possible to have in multiple motor with a lot of current, if we can put in parallel several GaN FET. That's the question.
Yes.
Yes. We don't have a reference design to show this, but we have customers which are paralleling 24 GaN FET per switch, and they have really, I would say, jumping motors in the real sense of the word. So, so that definitely, yes, the answer is yes, you can do it.
Okay.
I hope we can come also as soon as possible with similar reference design so that you can get it, test it, and copycat it if you want.
Okay.
Then there's another question from Suresh who's asking, do we have GaN-FET for high voltage? So our portfolio goes up to 350 volt DC bus, okay? And that's one thing I was telling, depends really on the application, but when it comes to motors and high voltage motor, I still don't believe, especially if you have high voltage and high current together, I still don't believe that we will stay in the future on a two-level inverters, because there are too many drawbacks on staying with a two-level inverter. So I may envision a little bit more going in a 3-level, 4-level, 5-level, depends, you know, where the market will go. And once you start going multi-level, you start getting a lower voltage switch is applied to higher voltage motor, and you get a lot of advantages in terms, especially from the motor side. So no, we don't have higher voltage than 350 volt. That's
Okay. All right, just wait a minute for any other questions. If there aren't any, or if you think of additional questions for Marco after the webinar, you can certainly send them into info@epc-co.com and we'll get them answered for you. So thanks to everybody for joining today and for your questions. If you will, you'll get an email in about 24 to 48 hours with a link to view a recording of today's webinar, and also copies of the presentation slides. So I think just lastly, be sure to register for the remaining installments of the Summer of GaN webinar series. The next one is September 1st, where EPC's Vice President of Applications, Michael DeRoy, will discuss how to design DC-DC converters with higher efficiency, smaller size, and lower cost. You can visit our website at epc-co.com for more information and to register. So thank you again, everybody. Thank you, Marco.
thank you, everybody.
Have a great day.
Thank you. Bye-bye.
Bye.